Moving the ball at an angle requires a bit of trigonometry and vector math. If the ball travels at an angle, let's say about 30 degrees, with respect to the x-axis, and has a speed of ball speed in that direction, which we also call its velocity, speed plus direction, that velocity can be decomposed into a velocity along the x-axis and a velocity along the y-axis, as in this vector diagram. The ball speed in x and the ball speed in y form a right triangle with the ball speed of all as its hypotenuse. Ball speed of x being adjacent to the angle and ball speed y being opposite to angle. So from the trigonometric ratios then, we can deduce that the ball speed in x is the overall ball speed times the cosine of the angle, and the ball speed in y is the ball speed times the sine of the angle. So in order to start the ball traveling at an angle, we will have to first pick a maximum allowable starting angle. If the angle is too large, it will take too long for the ball to reach a pedal. In the worst case 90 degrees, it actually be parallel to the net and never reach the pedal. So let's add the following to our constant section just here after ball size and ball speed, and say that the max angle we're allowing is 30 degrees. So we already seen that we need the sine and cosine functions, so we need to import those from the math module. But these functions expect angles to be in radians rather than degrees, so we also need to import the conversion function. We'll also, while we're at it, import the random module to access random functions down the road, because our angle, starting angle, will be a random choice. So let's go to the very top of our code up here, and just after the sys module that we import, we're going to import the math module. So, but we're not going to import the whole math module. We're just going to say from math, we just want to import the sine function, the cosine function, and the function that computes radians out of angles, so which is here radians. We'll also import the random module. So all we have to do now is pick a random angle at the beginning of the game on state, and which actually happens when we enter the key down event. So that is happening right here. So in our update game state, if the game is over or stop, before we enter the game on state, we're going to pick our initial angle. So so what we're going to do here is I'm going to pick the angle here, and it's going to be in radians, so we have to convert it from our original degree, and then we're just going to choose from the random module a random integer, rand int, and then from minus max angle to plus max angle. So I'll make this, I don't have to do the plus here, but just let's call this plus max angle, so that we see the symmetry here, right? So, and then, so what this does is I'm getting a random integer, converting that to radians, so plus minus 30 degrees, convert that to radians, and that's my angle. Now I can actually set my initial ball speed. So my ball speed x is then the ball speed times the cosine of the angle, and the ball speed in y is the ball speed times the sine of the angle. So that's the only other thing that we want to do is to basically pick whether the ball also goes to the left or the right. So we're going to have another element of surprise when we want to do that. So, and we can do this here by the following lines. So I'm going to pick the initial direction, and so I'm going to do the ball speed in x, which can be either left or right, whether it's positive or negative. So whatever I get, I just multiply this by the random choice of -1 and 1. So random dot choice of a tuple. So again here we get function call on a tuple, so that's why we have the two parentheses of -1 and 1. So we know how to bounce things now from the pedals by just flipping the x direction. So now that we have potential to hit the upper boundaries and the lower boundaries, we have to flip the sign for the y component there to actually do the bouncing of the top and bottom boundary. So let's add that just after we deal with the pedal bounce. So here's bounce the ball of the pedals and boundaries. So this is the code that bounces that. So let's do this here so that we got the two bounces before we have the other one. So let's do this and say, okay, if the ball collide rect with the top boundary, so it's going to be looking very similar, or ball collide rect bottom boundary. So then again, if it's the top boundary, then we have to adjust the ball top to be equal to the bottom boundary, the top boundary bottom, sorry, top boundary bottom, top boundary dot bottom. Right, so because the ball might have traveled into the boundary, so we just adjust it so that it's right outside of the boundary. Otherwise, we have to, we're colliding with the bottom boundary, so the ball bottom needs to be adjusted to the bottom boundary top. So in both cases, we flip the sign of the y component of the speed because that's now the component that is orthogonal to the actual boundary. So ball speed y is equal to minus ball speed y, just as we had the bouncing of the pedals. So that's it. We now have a fully functioning Pong game, and the only thing that's missing is the scoring. So let's run this. And here's our playing field, and let's go. Oops, and I've already missed it. Okay, so what we see, it bounces off everywhere in the manner that we need to, and therefore the whole thing works. So we got ourselves a Pong game. All that's left is the scoring.